Good morning, everyone. Welcome to the last day of GTC. And now that I know how to use this clicker, let's get started. Healthcare is fundamentally shaped by physics, right? So I want to anchor us as I talk about all these innovations to say this is not a net new chapter. It's building on the continuum that we've been on for last 2 decades at NVIDIA. But the industry itself, right? A century ago, with the invention of X-ray, CT, and ultrasound, medicine got its superpower, the ability to look inside the human body without cutting it. Then came image reconstruction, turning raw signals into images, and accelerated computing found its killer application. Then we moved into image-guided therapies, where imaging started assisting in the interventions and guiding the clinicians and the surgeons. Deep learning had a big bang, and we moved from an age of hardware-defined, rule-based sensor processing to AI that can now start learning physics. AI moved beyond the scanner to ambient rooms where it could understand, hear, listen, observe, assist, and that's been the age of agentic AI. And we're today at an inflection point. Right? All of this work leads us to the moment of physical AI, where AI can see, perceive, but act in the physical world. And we'll see that across embodiments, and it's all built on the same foundation. We'll see that across surgical robotics, some of the hardest tests of physical AI. We'll see it in clinical cobot embodiments, care companions, supply chain cobots, assistive humanoids. And this is really needed for healthcare. Think about it. We have 160,000 hospitals, 72,000 procedures, 8 million medical devices. And while all of this data, all of this sensor, all the devices can be digitized, care is actually delivered physically. So if we imagine a world where there will be all this assistance that can act, the permutation and combination of environments, the OR setups, the different devices, the kind of procedure types, warrant that there needs to be investment in simulation platforms that can allow for these robots to learn in new environments, allow them to acquire new skills, practice them before they can ever be deployed in the real world. So I just wanted to anchor us on the need in healthcare for physical AI. And why do we hear so much about physical AI here at GTC is because there have been 3 fundamental tectonic shifts that are laying the foundation for it. We in the healthcare team build upon everything else at NVIDIA. We get the privilege of standing on the shoulders of giants at NVIDIA who are building these foundations and build the healthcare derivatives of it. So the first pillar is world foundation models, right? World models like Cosmos can understand and generate complex medical environments. That's what the team has done with post-training Cosmos for healthcare, surgical scenes, and clinical workflows. That's the first piece. So you have world models. The second pillar is robotic policy models, like Groot and Groot H that were announced at GTC, that can now enable these robots to have policies that are generalizable across skills and can translate from perception and reasoning into action. And the third pillar is the physics simulation. We have very high fidelity simulation capabilities from classical simulation that is fundamentally an accelerated computing problem to now neural simulation and generative physics. And these proxy simulation engines are coming very close to real-world performance. This is what's happening across industries that's lending itself to healthcare to have its physical AI moment. And that's why for physical AI, so far we've always spoken about AI and the data challenge and the ability, whoever has the real-world data moat. Physical AI changes that. Because think about it, like in autonomous driving, we had all these numbers of hundreds and thousands and millions of miles you had to drive, right? But there is no way you can drive through every terrain, every corner, every edge case. So the way it is actually, there has to be a data flywheel investment to bring physical AI to life. It has to start with real-world data because you have to ground these models in reality, in the physics of the world we live in, and you get these pre-trained models. But then there's a continuous loop of post-training, an immense generation of synthetic data. Like I said, you could be generating this data with classical simulation techniques, which are well grounded in the physics of the world these models have to interact in. But lately, and more so like my colleagues earlier shared, there are neural simulation techniques and reinforcement learning techniques. But this is the flywheel that will allow a data gathering strategy to have these models in a continuous loop to learn. So it's not just about access to AI-ready data. It's not just volume. It's also that quality and coverage. And there's no surgeon, no hospital, no one hospital would have seen all the cases. So can you start leaning on these simulation engines to generate synthetic data to bring that diversity, which translates to robustness and transparency for these AI models? And the first investment we had to make was in this real-world data. So a huge shout out to the founding members of OpenAge who've been hard at it for the last 18 months. Axel Krieger, Dr. Nasir Nawab, Sean Hoover, Mahdi Azizian. That started as a conversation, has turned into one of the largest release of healthcare robotics data. Over 35 plus partners, the likes of CMR Surgical, Moon Surgical, across 11 embodiments and 750 plus hours of healthcare robotics data. This is the first investment we had to make, and now that all this data existed, we could actually take the vision language action models, like the GROOT-based models, which have essentially, right, there are two components. There's a Cosmos reasoning engine, which looks at the vision and language and understand the environment and intent to generate semantic tokens that are then ingested by the diffusion transformer with the robot states to create action-based policies or action tokens. And these models, if you just take GROOT out of the box, does not generalize well for surgical robotics. But OpenAge made it possible, right? So you have that foundation, and that's what we launched at GTC this year. GrootH is fully open source. It's available to get started on GitHub, to be the way it can be downloaded on Hugging Face. So that's great. You have real-world data. You've trained the action policy model that's getting us much better performance than zero shot of any of these generalist VLAs. But it's not going to be enough. And it's not going to be enough because of the post-training synthetic data generation loop that I shared about. You're going to have to train this model a lot more. And that's why the third pillar of our investment has been in NVIDIA Cosmos. The world models, the world states in which these robots have to interact, they have to be as close as possible to reality. So the first derivative we are releasing for Cosmos H is for transfer. It allows for controllable synthetic data generation. You could start in Isaac Sim Omniverse to bring real digital twin environments of the human anatomy that's grounded in the physics. So it's not generative AI that can start hallucinating. And then you can be applying surgical transfer to it to create variations of that world. So that is huge. Surgical Predict allows you to now start generalizing and predicting different action states. So it's many skills that can be in one environment. Again, it's a derivative of the foundational Cosmos Predict model from NVIDIA. And we've essentially brought it all the surgical data sets and the surgical domain understanding so that it can actually predict these different skills, practice it in simulation, and that simulation is very close to the real world. And finally, the surgical simulator. This is what the talk earlier explained as well. But this is a foundation model of a kind where we are now moving from rule-based simulation to learnable simulation, where you can evaluate these policies and so on. And for the aesthetics of the slide, we've always kept it to benchtop, but I was hoping the audience here would like to see some gory surgical videos, so I'll take that chance, right? From the left, what you're seeing are segmentation depth masks brought in from Isaac Sim, and you apply Cosmos transfer. And the right-hand side is a generative. It's a generative AI-powered laparoscopic surgical video feed. On the right-hand side, you see an image and a prompt to say, use the robotic forceps to puncture a needle into the soft tissue. And I have to admit, I'm an engineer. I have no surgical background, but the video on the right does show something looking like taking the robotic forceps and puncturing into the tissue. And the action-controlled, the Cosmos World Foundation model allows for you to bring these embodiments and build simulators that can now start evaluating different tasks across different policies in different embodiments. And that actually lays the foundation for how we see simulators for even some of the hardest problems like surgical robotics being solved. And all of these World Foundation models, the data set, we bring it and we anchor it into our platform called Isaac for Healthcare. So I'm essentially making sure you all know how is all of this being released to developers. And Isaac for Healthcare, NVIDIA Isaac is the robotic platform. Isaac for Healthcare are domain-specific extensions on Isaac. So what do? We go find what are the domain-specific hard challenges. It includes sensor simulation libraries, simulation and synthetic data generation pipelines, some of them leveraging the foundation models I just shared, and models and policies like Groot and others. We also publish in it end-to-end workflows, blueprints, developer recipes that allows anybody to get kick-started. And it's a way of translating all the technology foundations that NVIDIA has done in the 3 pillars that I spoke about, world models, action models, and simulation technologies, and translate that to use cases for the healthcare industry. So double-clicking on some of these domain-specific elements, we have sensor simulation libraries for ultrasound, right? That's allowing you to understand end-to-end simulation pipelines from tissue acoustic properties to probe configuration to be able to generate realistic scans using NVIDIA's optics. We also, at this GTC, have released X-ray sensor simulation that allows you to understand the end-to-end physics of that pipeline, from CT-derived volumes to ray propagation to detector response. And this allows you now to generate synthetic sensor data at scale. So it's a fantastic release, Isaac for Healthcare v0.5, sensor simulation libraries available today. In terms of the synthetic data generation pipelines, we publish these best practices. Some of you might be using Isaac and others, but a lot of them are for industrial AMRs and so on. And so we are really trying to close the gap for the healthcare developers. You can be building digital twin by bringing your own patients, because the world a lot of healthcare lives in is the human anatomy and the human physiology. And so you can be leveraging some of the models from Manai to generate synthetic MRI data. It can be grounded in a real-world CT scan. You generate a 3D mesh out of it, bring it into Isaac Sim, and from there you can apply Cosmos H, and you have this engine to be able to now understand the human anatomy and create all sorts of world states with that understanding. We have a pipeline to bring your digital twins. These are the physical environments the robots have to operate in, and it's the same pipeline. You create your digital twin, you bring in your digital twin assets, you can use neural reconstruction to multiply that, allow for those interactions and those environments to be permutated and combined in Isaac Sim, Cosmos transfer, and you have the same pipeline to essentially create the foundation for this simulated world for the robots to really learn to be robots. We have the surgical video generator that leverages the Cosmos H predict model that we just shared, and you can be generating your synthetic data out of that. And we also have a pipeline that leverages the robotic generative physics simulator. And all these pipelines are available to you today to just use them out of the box, and see how these technologies connect together. But we also publish all the post-training recipes, the pre-training recipes, the data sets we used for all these models. So you could be in the room and thinking, but this is all on laparoscopic procedures, and that's not my domain. It's fine. You could be taking all of that best practices and adapting these models to your use cases. And this is something how the simplest view that we could get to for the physical AI robotics workflow. Right? So you start with that pre-trained GrootH model that we spoke about. That's been trained with the open data set we've released. So you start with the pre-trained open GrootH model. And now you need to multiply the data and the environment variables and the world variables Groot has seen. And so you could do that with real-world data. That's fantastic. You could be doing that in classical simulation, by bringing those anatomical models from your CT and MR scans into Isaac Sim and applying Cosmos to multiply that. Or you could be doing it with other generative AI techniques. What you get out of that is a post-trained GrootH model that now understands, has seen more variability, but it still needs to practice new skills. Maybe it is pre-trained on suturing, and you needed to get to subtask autonomy of needle pickup. And so Isaac Lab gives that environment for that continuous reinforcement learning, imitation learning to acquire these new skills. And then Cosmos H simulator, that learnable simulator, can actually become the test bed for all these policies to be evaluated. And we shared in the paper that was published by Sean and the team that the policies like Groot, Pi0, and all other VLAs, when evaluated in this Cosmos-based simulator, mimics the ranking of real-world performance. That's really accelerating the development time. Imagine having to validate each policy on the physical embodiment in the lab. That's days and weeks. And here you have a simulator, and you can get that answer in a few hours. Once it's at real-time performance, even faster. And then you have the simulation engine, and you know exactly where the policy is not performing well, and you can go multiply more data. So this is all about accelerating the researcher and developer cycle. We've had the fantastic opportunity to working with some of the pioneers in the industry who are taking these technologies, seeing their value, and it's likes of CMR Surgical. J&J MedTech for their Monarch platform has built on Isaac for healthcare for their digital twin and are investing with Cosmos-based models for their data generation and AI model training. Moon Surgical, MedBot, XR Labs, LEM Surgical. Let me just highlight a few. Like I said, CMR Surgical has really pioneered that space. They could see the value of the foundations we are laying. They have come out and contributed to the OpenH data set. They are leveraging Cosmos H, the Cosmos H simulator, GrootH-based policy to start in their R&D space around subtask automation for their surgical procedures. And they're also leveraging the Holoscan and IGX platform. Johnson & Johnson MedTech is using Cosmos and Isaac Sim for their synthetic data generation pipeline. And it's been quite amazing in the last year. It's just been 12 months. This is how fast this field is moving. To see world models like Cosmos that understood roads and signs and our physical world, how well they adapt and can be post-trained to our anatomical and physiological world. And our partners are seeing some great success with that too. Moon Surgical is using Cosmos and Isaac Sim and Isaac for healthcare for system-level autonomy. So they're still in the environmental space, but they are able to import all the kinematics and the robot states to really get that system-level autonomy for the robot to get prepared before ever touching the patient. And so everything I shared so far was around surgical robotics. We believe that is the hardest test of physical AI, and that's why we wanted to apply our technology foundations to it. But it is the same foundations that go beyond surgical robotics too. And that's why at this GTC, we've really expanded Isaac for healthcare beyond clinical devices and surgical robotics into hospital automation. Project Rio was that. I hope you've all had an opportunity to see the demo. But it's essentially a recipe, a blueprint that developers can get started today to say, how do I assemble my digital twin? How do I create these assets? We have fantastic partners, the likes of Likewheel, SoftServe, who are masters at doing that. But once you've assembled that digital twin, you start your data flywheel, the data collection efforts, whether through teleop, through capabilities like MimicGen, Cosmos-based models, but you're essentially in that second bucket multiplying the data, the variations that the robot has seen, and then finally getting to policy training and the testing in the loop until you're confident that this policy can be deployed and I can take it to the real world. It's the same workflow. We've had the privilege. Veritas AI has shown this, embraced this as we've built it along, and they're showing it at the show floor. We have an amazing video with them, but they've fully embraced from Isaac for Healthcare, Cosmos H, this synthetic data generation to accelerate their development of bringing their Perry, that's the name of their humanoid, the Perry robot to the OR, and they've been doing their experiments and evaluations with Advent Health. So this is not sitting in a lab. I think all these customers we are sharing about, this is out of that, and we're really we're hoping, and we absolutely believe 2026 is the year that we're going to see the deployment challenges and the age of deployment coming for these robots. And so, okay, you get the data set, you can generate all this new data, you can make the robots learn new skills, but it's all in simulation. But the rubber really hits the road once you're in deployment. And one big release we are having is with Holoscan 4.0. It is the ultimate deployment stack for physical AI. I would say it's physical AI native, and there are 3 key features that make it so. It now supports EtherCAT that allows you to have these control to control the motor of the robot directly. It allows interoperability with the likes of ROS2 and GStreamer. So it's not a completely new stack. It's very interoperable with your existing development stacks, hopefully. And it allows for GPU resident graphs that are fully accelerated on the GPU with no interventions with the CPU, allowing for that speed of light, lowest latency in that deployment time. So Holoscan 4.0 was released at GTC. Folks in the room who are roboticists, who are thinking of their next design platform, please go check out Holoscan. And the ultimate combination is Holoscan running on an IGX Thor. This is our industrial-grade edge AI platform for real-time safety certified compute for robotics, devices, factory automation. IGX Thor really matters because it has 8 times more compute. And I just want you all to take that in. Everything that I spoke earlier about these VLMs and VLAs and Cosmos-based models, all of that AI is going to land on an edge computer. And so edge device design choices are being made now, and you want to have your AI platforms and your devices future-proofed for this age of AI. It's no more in the age of CNNs. Right? So IGX Thor and Holoscan 4.0 is a fantastic platform, which is absolutely physical AI native. And this essentially makes the same point, right? What we're doing with Holoscan is you have this speed of light latency. And then sometimes you hear, but I don't need it to go that fast. That's not the point. The point is how much more can you do in that latency budget now? You could do a simple CNN and a detection model. If you're here at GTC, you're seeing where the field is going. And the models of the future are not detection CNNs doing singular tasks. They are the VLMs, they are the VLAs. So you want to future-proof those platforms, and Holoscan is built for that. All right, this is everything I shared with you. This GTC has been about our healthcare physical AI platform coming out. We have released the OpenH data set, amazing foundation models, all the simulation best practices, recipes packaged in Isaac for Healthcare. But there's one critical piece, and that is that as you're thinking about in robots how they have sensors for perception of environment, robots that have to operate inside the human body, their perception is medical devices. our good old CT and MR and ultrasound sensors. And so I just want to quickly touch on some of the new models we're releasing there as well. These are our medical AI models, but they also come together in service of physical AI because a large part of domain-specific physical AI is inside the human body. And so for NVIDIA's medical imaging open models, all built on Monai, hopefully you've heard of that. We have segment family, we have a generate family, reason, and raw to insights. This GTC, we are releasing some key updates to that. Introducing the NVIDIA raw to insights for ultrasound. This is the first time you are hearing about how we believe and where we believe AI is headed. This is AI-based physics sensor processing, so directly from the sensor to recon. You have physics-grounded AI from the raw RF signal. It can, in real time, do patient adaptive imaging. It's production ready, and it was all built in collaboration with Siemens research team, with Altera, and NVIDIA's IGX. And the HSB really allows for that intervention of the raw RF data to be able to train this model. So the key takeaway is that AI is getting to a point where it can start understanding and deriving insights from raw physics. And maybe there is a lot more insight in that sensor processing that gets lost by the time it's in the imaging domain. So please take a note. GTC 2026, you heard the first time about raw to insights, and we'll be sharing much more about that in the coming year. We're also introducing raw to insights for MRI. This came out of our challenge in MICAI with the CMR X Recon challenge. The foundation model delivers consistent, high-quality reconstruction across scanners, protocols, and sites. It's shown its robustness. It's #1 on that leaderboard. And the point, again, is that for all the medical device developers, researchers, and as you guys are thinking of where's innovation in that recon pipeline, we really think this is the moment. Just like in 2017, 2005-06, where CUDA was discovered for recon, this is the moment that AI is really going to come to the raw physics sensor domain. We're also introducing Generate for CT and MR. It's a state-of-the-art 3D diffusion model for CT and MR scanners. And this one's amazed us, by its interest, by all the customers that we speak to, but also the kind of use cases. So as an example, when we have to bring anatomy into digital twins, there's a lot more CT data out there. Generate allows you to take a CT image and actually generate a higher quality, more resolution MR image, which is still grounded in the anatomy of the use case. And all these generating models are not meant for any sort of clinical decision making. That's not where we think the use cases are. This is all in service of diversifying the data sets as you train these new models and modalities. NVIDIA's medical imaging open models are integrated into Hopper's AI Foundry. So if you've heard of Hopper, they are here. They have an AI Foundry platform where they host their foundation models like Curie and others. And NVIDIA's open models are integrated in that. It's a great place to get started. I see Robert in the audience, so in case you want to learn more about Hopper. And we're also seeing integration with the likes of Philips, where they're taking all these foundation models like Segment, Generate, Reason, these open foundations, and post-training it with their scanners, their specific scanners, details and settings to really get the value for their use cases. So a huge shout out to Philips as well. Lastly, I shared a lot, and then there's just 2 places where you can get started to soak it all in, to get started. It's the GitHub NVIDIA MedTech. That's where we are hosting all the open models. The source code is all under Apache 2.0. We've released the pre-training scripts, post-training scripts. We're really wanting to move the ecosystem forward. So we are sharing in real time as we are learning. That's up there. Hugging Face is where we are hosting all the weights. OpenH is also available on Hugging Face to download today. And Isaac for Healthcare GitHub is where you can see how all these tools and technologies and models and data sets can actually be applied to post-train for your use cases, for your applications, whether in surgical robotics, in clinical medical devices, or for hospital automation, any kind of embodiment. With that, thank you all for your time today, and I'll take questions.
Thank you, Purna, for the talk. For people who have questions, please line up at the microphones that are here in the aisle. And we'll go first person over here.
Okay, my question is about autonomous surgery. When do you think this is going to happen, and how much governance hurdle you think the world has to go through? It will depend on the countries.
Excellent question. Surgical autonomy, we believe, is the absolute North Star in surgical robotics for it to come. So that, we believe, is long way out. What we are seeing is subtask automation, subtask autonomy, and I think our partners like MedBot, if you go to SRS and other conferences, they have very grand visions about it, even at their talk at GTC. MedBot is one of the pioneers who's taking some really innovative leaps. In terms of the regulatory stuff, it does come down to which countries are we talking about, and it really, the word autonomy has a large gamut, and so it really then comes down to what is the subtask automation and where those guardrails lie.
Thanks for the talk. With these approaches where you're passing the raw data to the models, do you have some kind of a hypothesis about what might be missed in the non-raw approach, or any kind of early hints of that?
I would say we are still in early research to even say that as we pass the raw data, can it even start understanding the acoustic behavior and the behavior outside of the imaging domain. The domain is getting accelerated sooner, and I think we will be at a point where we'll be able to show what's the before and after. So like the Siemens ultrasound data set and the model that we're sharing, as it gets applied further, like what was missed in the before approach, that now that this AI can understand all the sensor physics, it's able to augment or predict. I think that's still TBD, but I do think this would be one of the most interesting topics in some of the academic conferences. I highly recommend you connect with Sean Hoover, who's sitting right there, and he's leading a lot of this work.
Okay, great. Thanks so much.
Sure.
Okay, also related to this question, the model that you just showed, going from the raw data to image domain, you have several different kind of physical sensor, right? Are they based on the same architecture? I mean, the model itself, or it's a different model to do the different raw input data?
Currently, what we are releasing in the two model variants we have, so for ultrasound, we are releasing a model architecture, which is trained with the OpenH RF data that was contributed by Siemens. We don't believe that the model architecture will be changing based on the physics sensor modality, but as we continue to build upon it, we'll share more. The raw to insights for MRI is a completely different architecture and actually solving quite a significantly different problem. It's actually getting into the more recon approach, like an AI-based recon approach, as compared to just a CUDA-based recon approach.
Okay, thank you.
Sure.
Hey, good morning. I have two questions on the Cosmos H, the data generation. So number one, so how long can it generate the data, like for seconds, for minutes, or hours? And the second question is the user able to configure what type of data it can generate? For example, can it generate the data for a successful task or for a failed task?
I followed your first question. Can you repeat your second question?
Sure, sorry. The second question is, can the model generate a task, the data for a successful task or for a failed task? Or is the user able to configure that?
Got it, yeah. Okay, so for your first question, how many hours of Cosmos data can it generate? Like as much compute as you can throw at it, right? So it's not limited by, it's only these many seconds of clip or so on and so forth. So that hopefully answers the first part of your question. And your second part, it can. So your second part of the question is it able to only generate cases of successful tasks? That's not the case. Indeed, Cosmos has surprised us with its ability to learn physics, even just by the videos and so on. So it does need that constant prompting and post-training loop, right? So it's not like you generate all the data and you train Cosmos and you're done. You generate data, you train Cosmos, you prompt it for the corner cases you're looking for, and is it quite getting it, not getting it, and you might have to try different approaches for it, but it absolutely has shown that it can learn the physics and actually generate cases that it hasn't seen, and that's really the point of Cosmos, right? It is meant for those corner cases, and so as rich as an input you can give to it, we've seen it performs well, the best. It performs well in all these different variants, but it really performs really good when you have the anchored digital assets from CT and MR that I shared earlier with you. That really grounds it in the physics of the world that it's trying to learn about.
Okay, thank you.
Sure.
Hi, this is Suresh from United Health Group. Thank you for the talk, and it's exciting to see how much physical AI is progressing. Obviously, I'm part of the division in pharmacy, so I'm interested to leverage some of the world models like applicability, and I definitely connect with you. And I also let our colleagues on the healthcare side, like where we can leverage that. So, do you know who I can contact, or can I connect with you directly?
Yeah, I mean, you can connect with me. We have an amazing NVIDIA team here, so we can maybe chat afterwards, and I'll get you connected with the team.
Okay,
Sure,
thank you.
Suresh. Thank you.
Hi, thank you for the talk. I have 3 questions. The first question is, how do you, when you go from a simulation to deployment, something is going to break. So in your experience, what is the first thing that breaks and that simulation is still not able to capture completely?
What is the first thing that breaks? I think sim to real is not a solved problem, right? We are also making those endeavors, and some of the first things that break are because your digital twins are not physics consistent and accurate, it's system level issues that we end up seeing with the port connectivity issues. So it's not a seamless switch today. I think that's what we're trying to work out with. I don't know if you attended the earlier talk where Madhi and Sean shared with the HoloScan. So if you are building your pipelines with HoloScan, then you can test that deployment in simulation. And if you take that same stack, our goal is to minimize that gap of sim to real deployment. It's very hard to say what is the one thing that breaks, but too many things break. And the reason they break is that it's a completely different stack, right? So there still has a lot of bespoke work to be done as you translate all that simulation learning. But I would say that's much more on the system and the network and the system connector side of the thing.
Thank you. My second question is that if you have 2 systems, one system is trained completely on simulation, tested in phases, and then deployed. And then you have the second system, which is more traditional and conventional. And you test it and you build it and test it in phases with real-time deployment. At the end, which system still performs better? Or what's the difference between the completely simulated system versus the tested in real-time system?
I don't think the conversation will be so much about systems that are fully trained in simulation and systems that are trained fully with classical approaches. So as an example, maybe we can anchor the problem a little bit. So if you had to say, I believe today surgical robotics, for their simulators, these companies pay multi-million dollars for that very accurate simulators, right? But we have to start now adding the variables. It's a cost variable. It's a development variable. It's potentially a multi-year approach. So just to create, using classical simulation and computing technologies to create a accurate simulator for a procedure, much more costly, many years of deployment, development. And then in deployment, I'd say, considering that is the only system that's used in practice, the fidelity of the system is good, right? Now, if you come to what we shared, for instance, with the Cosmos 8 surgical simulator, the development and the cost times are reduced by a magnitude. And our early work is showing that the behavior of the policy ranking is quite close to real-world performance of those policies. So we don't believe a world where all the classical simulators will get replaced by this. We believe that the people and the pioneers who've been investing, the likes of surgical sciences who are building these classical simulators, will converge, and there will be a hybrid approach, and there will be some aspects of that tool-tissue interaction or some aspects of that physics that you will need classical techniques. And there will be some aspects of that accelerated development where a close proxy from a simulator is good enough, right? But our hope is that that significantly reduces, the cost and the development time it takes to build these high-fidelity surgical simulators, which allows for the technology to grow faster and expand faster into multiple procedures and so on.
Got it. So a hybrid approach, right? I know.